Hello and welcome to IEEE Soft Robotics podcast. In this podcast, we're going to interview researchers from both academia and industry about their work, thoughts, spectrum, and more beyond that. This is Marwa Edwini, and I hope you will find this podcast useful. If you would like to connect with us, simply send us, and we will be happy to hear from you. And here is my interview. Thanks.
So maybe quickly, if you can introduce who you are for people maybe first time listening to you, how would like to define yourself for people who listen first time? Yeah.
Define myself. Well, I think, most relevant probably is my name. I'm Oliver Brock from Technische Universität Berlin. I've been doing robotics for, I guess, a quarter of a century now. And I guess the reason we're here is that maybe 14, 15 years back, I was exposed to the ideas of soft robotics and immediately took a liking to those ideas and approaches. And I guess my lab has been researching on soft robotics ever since.
Yeah, great. So maybe I can ask you, since you have this experience, so far till now, what could be still hard questions, still not really touched by the field? Because we have the paper, Hard Question for Soft Robotics. I assume you see it already. But when you look back from 15 years ago till now, what are you saying still, in the field, we're still not touching this point. Still, there's not much work here.
Well, I think that probably we're still missing most things. Our field is a very young field. I think robotics as an academic discipline has probably existed with that name for, 60 years. Compared to physics with many thousands of years of a history, that's obviously very young. And if I zoom out all the way and think about how in 500 years from now we're going to perceive our field, I very much do think that we're going to have advanced a lot, and that we're going to see how right now we're very influenced by the other scientific disciplines around us, and that we're kind of trying to compete with them intellectually and also in terms of funding, and that has very much driven our vision. And I hope that very soon we'll get to the point where we can define our own discipline, right? And we can define our own set of basic truths upon which we can build. Maybe something like Newton's laws of motion certainly have advanced physics in significant ways. It would be difficult for me to articulate what the corresponding laws in robotics would be right now, but I do think we will discover them, right? I think right now we're drawing from other disciplines, physics, mechanical engineering, mathematics, and so on, right? We're drawing from the existing disciplines to advance robotics, and my feeling is we're just in the process of discovering our own foundation that is really unique to robotics. Even if you look at a robotics textbook, you have kinematics there, you have dynamics, you have control theory, right? Many of these things are borrowed from other disciplines, and so hopefully at some point we'll have things that are unique to robotics.
That's a very good point. You mentioned many interesting points, but maybe what does it take so that we can make foundation for the laws related to soft robotics? And I think you interested about co-design or designing for soft robotics. And when we look to design of the design recipe or methodology, or why we designed this design, for example, what does it take that we can achieve that? You mentioned funding. Do you think funding is a constraint in that case so that we can go in that direction? What other constraint do you believe?
I'm not sure if actually right now we're experiencing really significant constraints. I think robotics at this moment in time has very good funding, and I think what it probably takes is patience. So you mentioned co-design. I think what we're discovering, or what soft robotics really was about, which kind of provides the framework and the context for co-design. I think basically we had the digital revolution, right? Computation was automated in a way that radically changed the way we approach many things, right? CPU, von Neumann architecture, all of these, having tiny computers now that can do more computation than humanity was ever be able, throughout all of humanity we were able to do in 1 second, right? So that has really influenced in a very, very good way many of the scientific disciplines. I think in robotics, what is happening now is that we're discovering what humanity has done for thousands of years. That was use materials in our environment that are tailored to a particular task and put them into a morphology that is helpful, right? So we used stones for blades, we used wood for the stick, and so on, right? And we built a tool that would allow us to cut a tree, or I'm just making this up, but this is something, in some sense, humanity has done soft robotics from the very, very beginning. And my feeling is that we're now really were, and justifiably so, preoccupied with this amazing technological revolution that was the digital computer. And now we're discovering that in addition to the things we can do now with digital computation, which is characterized by the Turing machine and by a lot of math about computability, we're now adding back into the mix, right? This is something that we've done for a long time, and we're adding it back into the mix, the fact that we can design material properties, we can design the shape of objects to achieve a certain functionality. And now putting those two things together now, I think will give us another boost, right? Maybe even comparable to the boost that we got from the invention of the digital computer in terms of robotics, in terms of bringing together these two computational paradigms, right? One is this computability, Turing machine paradigm, and the other one is a clever design, morphology, shape, material properties, kind of building objects that fulfill a certain function design approach. And by bringing these together, I think we will see that we can solve problems by dividing them into two pieces. The one piece that's done by the hardware and the one piece that's done by the software. And if we learn how to make that dividing line, then the problems should become much simpler, right? Because we solve the computational problems with digital computation, and we solve the morphological problems with morphology. And by definition, that is a good idea. And I think that we will see robotic systems that combine these two things in very ingenious ways to achieve incredible robustness, incredible versatility, and overall, will allow us to explore additional applications. And so this is exactly, at this boundary, is exactly what co-design is trying to do, right? We have no idea of how to draw that dividing line. We have a set of tools for designing hardware. Let's, for simplicity, call it mechanical engineering, right? Or civil engineering, right? I mean, we have all kinds of branches of that, building bridges, building houses, building cars, and so on. And we have a relatively young branch of science which is concerned with digital computation. And we don't really know exactly how to bring these two together. And I think co-design right now is starting from the idea to acknowledge that, to say we don't know how to bring these two together really well. So let's start with a very simple approach, which is just to perform optimization over this combined space, right? In a very simplistic way, not driven by a lot of knowledge of the problem, but by applying this to easy problems. Hopefully we can start learning something about how to solve this. And maybe the knowledge about how to co-design will be a chapter in this new robotics textbook that will write in 50 or 500 years, that really contains things that were contributed by roboticists for robotics.
I really like this point so much and very important. And I'm curious to ask you, Oliver, in that case, do you think if we look in soft robotics, we want a certain material with certain characteristic? And you mentioned in evolution, we don't know how this material, for example, multi-material, how this structure already came up in evolution. Do you think intuitive design in the beginning is earlier process before going to co-design so that we can understand what actually we need? What do you think this kind of, you say that there's something in between, or still we don't know how we can merge two? Do you think intuitive design is a beginning of this a step to design this material in a certain way, and then you can figure out what's really significant? How do you see this process?
Yeah, I mean, I totally agree with you, right? We have extensive experiences in designing artifacts, and we have significant experience in using digital computation to control things, right? So we have experience in both domains, and we have experience in making robots do things, which in some way is combining these two things, but in a very specific and well-defined interface, right? So if you look at traditional hard robotics, the role of the robot and of control is to eliminate physics in the robot, right? We compensate for gravity, we compensate for centrifugal Coriolis forces, we compensate for inertia. So we try to make the robot behave like a unit point mass, right? And that's when we think we can really control the robot well. And it's true, right? Once we have abstracted away all of physics, the robot becomes very easily controllable. But the hardware has been kind of limited in its ability to do things to just doing what control wanted it to do, right? So I think this characterizes robotics for several decades, that the hardware was just in service to control. The hardware had nothing to do. It had to just follow the commands. And I think this is now changing. And so the question is, how can we change that? And I totally agree with you. A very good starting point is our own intuition, is our experience in both the control and hardware domain. And I think we can start from things that we know how to do and gradually increase our search space over which we search for co-designs. Right? To do co-design, we need a space of control policies. So I think it's good to start from what we know, and we need these two design spaces, right? We need a design space for control, and we need a design space for the space of all controls that we want to consider. So these two spaces initially should be simple, so we can start learning about how to develop co-design. And how to make them simple is to use our intuition, is to use the things that we know, to not allow for all arbitrary arrangements of physical bodies, right? You know, to sort of put random voxels together of 2 million materials, but to say, well, maybe we'll start with kinematic structures. Or maybe we'll start with very simple volumetric representations. Maybe we'll start with parametric representations of fingers or of limbs and so on, right? And many people have done research along those lines. And so it's a good thing that we have full control over the space of all possible control programs and the space of all possible hardware. And so we can adjust the difficulty of the problem. You mentioned evolution, right? Evolution is kind of progressing in a relatively unconstrained space, right? That's a huge, difficult optimization problem. I don't think that should be the first thing that we do. I think we can pick something very small and see where that takes us. And I think the key is that we actually bring these two spaces together, right? That we start exploring where to draw the boundary between control and hardware.
When we look to maybe evolution, we see that certain animals have, for example, tougher material or material with certain characteristic. And when we look to soft robotics, from your perspective, do you think there's something still missing on the material or the morphology, whatever, something you think this is missing here, or this functionality or this properties in the material is missing? And maybe co-design could help in figuring out how we can come up with this design.
Yeah, so I totally agree, but to me that's kind of more of a long-term perspective. I think with what we have right now, with the robots we can build, with the sensors we have, with the actuation, with the control, I think we are in a pretty good position to explore and understand the co-design problem itself. we will get in all kinds of directions to boundaries where we say, oh, I wish I had lighter material, I wish I had softer material, I wish I had stickier material, I wish I had this sensor and this actuator. So we will hit boundaries. But I think given what we have right now, we have enough capabilities in all departments to really explore co-design. And in some sense, these explorations can lead us to the bottlenecks in these other subfields where we need to then focus our efforts to remove constraints that prevent us from even advancing further. But to me, the first step is to, given what we have right now, to explore the computational aspects of co-design, right? So, and in computation, I include morphological computation and digital computation, to understand the whole problem as such better. And then it will lead us, given a particular application, given a particular design goal, it will lead us to the places where we're limited by, like I said, sensing, computation, material, and so on, right? So I think to just without a real focus in mind, continue to develop new materials. That's what material scientists do, right? And I'm very happy that we have them to do that. But as roboticists, I think our goal is to take what they have produced, to do the best we can with it, and to pose new problems also to the material scientists as to, this would be a material property that we would want to have in this polymer. So I think our role really is not to take away the job of the material scientist or of the control theorist, but our job is to study what happens when all of these things come together into a real system.
Wonderful, yeah. But when it comes to limitation in morphological computation and also the digital computation, recently, what point do you think this will not really fit? Because we speak about sometimes the technique we use is not really fitting the nature of the soft materials. Sometimes if we speak about different material classes, but the nonlinearities and large deformation, there's a lot of issue about that. Where do you think maybe we can push here in advancing the digital computation, for example, or morphological computation? Do you see any downsides so far can be touched again and explored?
Well, I don't see a downside because I just see it as really an additional tool at our disposal. Right? I mean, we can still just go back to industrial robots made out of steel with very sophisticated control. They can move very repeatedly and robustly to sub-millimeter accuracy. So we have those tools. If an application requires that we use those tools, hey, we know how to do that, right? But there are all these other applications for which industrial robots are not very good. Right? I mean, starting with medical applications, starting with human-robot interaction, and so on, right? There are many, or also general manipulation. And it's these problems that we've tried to solve with the mindset of put 100% of the responsibility into the control, and then the robot just does what it's supposed to do, right? I mean, in some sense of grasping, in some view of grasping, the only task of the hand is to place contact points at a particular point in space, right? And I think the right way of grasping is to look at the hand as something that touches the environment, that slides along objects, that pushes objects, and so on, right? So there's a much richer set of interactions. It's not about contact points. There are always contact patches, and it's about the constraints that these contact patches provide. So this is beginning to talk about things where we need soft robots because we want to have contact. It needs to be safe. We don't want to destroy the environment or the robot, and that's where we start to discover new things, right? So I think we will not throw away anything that has happened in robotics. We will continue to use it. We're just very rapidly expanding into new areas, discovering new views, and then new tools to solve problems in very different ways, and I hope much better than we were able to do before.
So you mentioned the finger, and I think how we can design them in a safe way, because we speak about embodied intelligence. And do you think how do you see that embodied intelligence so far in soft robotics, and what could be limitation for soft robotics to achieve embodied intelligence? Do you think, should we use this kind of natural physics in the material so that we can play with different multi-material, for example, to have different stiffness? I don't know, how do you see the embodied intelligence? Should we focus more on the body itself or maybe external things? How do you see that?
Yeah, so the question is, how do you want to define embodied intelligence? And there was a really wonderful workshop. I think it was even called Embodied Intelligence Workshop, right? Yeah, I thought it was really a great meeting, and but I mean, thankfully, much of the discussion was revolving around what is really embodied intelligence, right? So I think we're still struggling as a field a little bit to really understand what that means. Everybody has an intuition, but really it's difficult to put the finger on it. And to me, somehow embodied intelligence and co-design are very closely related, right? We have intelligence and embodiment, and somehow these two things are put together. So to me, intelligence, I think, is the attempt to express what we think is biologically intelligent computation. And then embodiment says, is kind of acknowledging not all of that computation is happening in the brain or in the nervous system. Some of that computation happens outside of the brain, outside of the nervous system, in the body, or maybe even in the world. And this is where co-design comes in, that these things clearly interact with each other and enable each other, right? I mean, for example, in visual perception is a very strong and important sense in humans, and our retina has probably dozens of task-specific feature detectors. So the information that comes out of the eye through the optical nerve to the brain isn't really an image as we imagine it with pixel by pixel. It's already been filtered to a significant degree for information that allows us to survive. So in some sense, the retina is our embodiment that has encoded the learnings of evolution to allow us to operate our visual system in a much lower dimensional space, right? And so it's only because the body and the mind, I mean, not to extend the life of that unfortunate dichotomy, but the body and I don't know how to call it, right? Because those two things are so intertwined, and we don't really have the words for it to express their interaction as a thing in itself. But it's only because all of these things come together we can do such robust vision. And the same thing is true for locomotion. The same thing is true for manipulation. There are many people that believe that all of our more abstract thought is ultimately based on super sophisticated but basic capabilities to represent and perform motions, right? And that even terms in mathematics, like recurrence, is a Latin word for to run in circles, basically, right? So we have very strongly embodied metaphors and words even for very abstract concepts. And so so it's possible that understanding this very basic interplay between body and computation really will allow us to uncover the basis upon which the higher cognitive functions are built. I actually believe that, right? I actually believe, and the simple argument would be evolution that you mentioned, right? It's clear that in the course of evolution, animals, before they developed the ability to play chess, learned how to move about, how to detect predators, how to detect food, how to approach food, how to fight, and all of these things, right? We had to incrementally build our skills on the things that we already knew, over evolutionary timescale. And so I think that the path to understanding really these high-level cognitive abilities, what we call intelligence in humans, really will lead through an understanding of how this interplay between body and thought, or body and mind, or body and computation, or morphological computation and digital computation, how all of these things actually play together to produce behavior. Because that ultimately is the goal of robotics, and it's the goal of evolution, right? To produce biological agents that behave in a way that ensures the survival of the genes.
Wonderful. But I'm curious to ask you this question, because I think in the field we speak about physical intelligence. This is a term we use already. But the idea that we can use this geometric and material nonlinearities to perform a certain behavior for the material without using controller. And the other side, sometimes we use like minimal control, just not to destroy this natural dynamics in the material, and how we can really extract them, understand them. How do you see, if we speak about physical intelligence, the body itself can manifest intelligence, like that fish swimming upstream, for example, that one example. How do you see that? Do you think it could be achievable for soft robotics to depend slowly on physical intelligence? How do you see that part?
Yeah. So my feeling is right now we're approaching our understanding of the interaction of an agent with the physical interaction of an agent with its environment, like let's call it the body with its environment, still from a perspective that's very much motivated by traditional robotics. We're trying to really accurately model soft robots. We're trying to come up with models for soft materials. So we're kind of doing what we know how to do. But it's clearly a much more difficult problem, right, than to model steel parts, because steel is very stiff. And the question is, do we actually really need it, right? And my feeling is that we don't. My feeling is that we need to model not the soft body itself, but we need to model the task success relevant aspects of the interaction, right? And now you could respond, well, from the traditional robotics perspective, well, yeah, that's just a physical simulation. If I super accurately represent the soft material, and I super accurately represent the environment, and I can simulate the interactions, then, Oliver, I will have exactly what you're asking for. And that would be true if it were possible to do that, right? But the problem is that we don't know which phenomena to simulate. We will never have accurate models. We will never have really accurate physics in some meaningful way that is accurate enough and responds to corresponds to what we need. And here's a brief argument why I believe this to be the case. So if you take a block of, let's say, silicon rubber, and you want to simulate that accurately, we can try to come up either with approximate models that say, I'm going to represent it as a point with certain extensions, and I'm going to make, great abstractions. That obviously already, we're out of the game. We've lost the ability to super accurately simulate the interaction with the world because we're not really representing our robot correctly. And then the alternative is, that these are the two alternatives we know right now, are kind of discretization based models like finite element methods, where we have to, again, we could say we pick a discretization that's very small, and so we get some accurate, and finite element methods are very accurate, right, and very, very useful. But my point is the computational paradigm of material. I can get 2 kilometer cube silicon material, and all the computation will happen at the same speed as if I had a very small cube. But if I want to simulate this at the same accuracy, then I can't do it with FEM because 2 kilometers is huge. I have so many elements in my mesh that I cannot simulate it. So this goes to show that the computational paradigm of material and the computational paradigm of digital computation are fundamentally different and cannot solve the same problems with the same ease. So if we're trying to simulate the body, then we're ignoring this. We're saying, oh, I can use digital computation to just emulate this additional computational paradigm. Well, nobody would say that about quantum computation, right? Sure, I mean, in principle, you can factorize a large number with a Turing machine. You just would have to have billions of years of time, right? So that's not very practical. And this is also why I'm saying it's not practical for us to take digital computation and to simulate the body in this way, right? So we need to understand something much more fundamental before we can think about simulation, because we won't be able to simulate all of physics. We only can simulate the physics that is relevant to the task, and that is the key, right? How do we get to that? Well, we got to try this and gonna try that, and we got to learn this new representation, right? It's not a geometric representation that really presents the shape. It's something that represents interactions in a context of a task. And honestly, I don't know what that is, but that's, I think, what we need.
Excellent point. Thanks so much for highlighting this point. I totally agree with you. But maybe I'm curious to ask you if there's something, maybe through your work in the space of co-design or maybe simulation, I think, and representation in reality was counterintuitive.
Well, okay. So actually, maybe I can relate to your point. So counterintuitive. I wouldn't call it counterintuitive. So what I've experienced is surprise, right? It's surprise to say, well, really that works so robustly. That simple thing actually can do this and this and this and this. That to me is surprising. So that in some sense that violates my intuition, and so you could call that counterintuitive. But it's my intuition about hard robotics, right? It's not my intuition of physics. It's my intuition of hard robotics, right? I mean, if you have a hard hand and you make it go through a particular motion and you replace the object with another one, you don't expect it to work, right? And with soft hands, that does happen for significant variations in object shape, object weight, surface properties, object size. And that to me is super intuitive relative to traditional robotics, that you can come up with something very simple that works under a very wide range of circumstances. But I think that's just to make the point that there is something really fundamental happening in soft robotics, that really the power that we can leverage by using the body the right way is amazing. Right? And I have to admit that me too, I come from a computer science background, right? I mean, for the last 30 years, I've been dealing with computers and digital computation, and all the problems I've learned how to solve, we've solved with algorithms, sorting and graph algorithms, right? I mean, that's what we learn, and that's what I teach students now, right? I teach them algorithms. Yeah. I think we need to teach the mechanics too.
I totally agree with that. Absolutely, yeah. So maybe because we close the end, I have a few questions. Maybe through your lab, what could be still harder challenges to you? Saying, yeah, still very hard to tackle the problem. I don't know what kind of hard challenges you still, don't figure out here.
So actually, I think the biggest challenge in robotics, and in particular in soft robotics, is that it's all the problems are not single person problems, right? It's the problems are too involved, and they require too many different levels of expertise to just have one person, solve manipulation. And so I think it is a continuous challenge to kind of raise to kind of hire the right talent, to define the right problems, so that all of these things that people do kind of fit together somehow. I think that is kind of maybe even a consequence of academia, because people do PhDs and then they graduate and then they leave. It might be much simpler in a company where you have people that work, for 20 years, and you can really build a team, and they really get used to working together. There's engineers to do the infrastructure, right? All of this is a little bit more difficult in academia, but this is compensated by the fact that you get brilliant, enthusiastic, motivated, creative people that come full of, sparkling with ideas, right? And there's always an influx of new ideas and different people, and so it's a very dynamic environment. I mean, I very much like it. Obviously, that's why I am in academia, and yeah, I think that having undergraduates and graduate students and PhD students there, without that, I could not imagine doing research. Yeah, I mean, if I had to do it, I mean, it's obviously it's them who do the work, and it's really in the interactions that happen between all the people that are there that progress is made. So, yeah, but I digressed from your question. So that I think is kind of one of the big challenges. And if I had to give you an academic challenge, like what's a problem to work on, I would, unfortunately, because maybe it's too expected, really say co-design. Although I have to admit that I don't really know exactly what that means yet, right? But it is basically the fusion of the power of the body with the power of computation, and to do that fusion in such a way that you really leverage it to the max, right? And I don't know how to do that. We have some instances, some points in the co-design space that show that there's amazing performance possible. But I don't think that we have a very principled approach to it.
So I don't know if you have a moment of doubt sometimes if you have no idea. You mentioned co-design. I don't know if you have a moment of doubt with the way of, of the ideas you have. How you deal with doubt? Do you have doubt already about some ideas you have?
Yeah, I don't think doubt is a useful category in science. You doubt is kind of it's unclear whether it comes from the subject matter itself, or from your personality, or from your mood, or from something you ate. I think that what is constructive in science is to have an idea, to listen to your belly, right? Is this a good idea? If it is a good idea, to go for it 100%, which doesn't mean turn off your brain. It just means you're dedicating to this idea what you need to validate it. You need to always have a slight degree of paranoia, right? You need to question yourself, and I guess maybe you could call that doubt, right? And then if that's what you call doubt, then I totally agree. Doubt is super important. You need to always question yourself. You need to always question your assumptions. You need to always think of alternative interpretations of the things you've observed, not just the first thing that comes to mind, because confirmation bias is everywhere. Right? You need to be suspicious. Right? You need to always think of what other explanation explains what I see that doesn't match what I want to see. Right? So maybe I don't know. I don't know. Doubt to me. Yeah, let's call it doubt. Yeah, you always need to doubt yourself. Let's call it doubt. Yeah, I think that's very important, but it shouldn't be discouraging, right? I mean, the doubt shouldn't be that you question your abilities, or that you hesitate, or that you need to love the idea, right? You need to love the process, and you need to love the idea. And if you do that, and then you're not disappointed if you disprove your own idea. That is also a very exciting moment, because there's no point in your research where you learn more than when you disprove your own idea, right? That is really a moment of enlightenment. And sure, it includes disappointment because you think you could have made the next deadline and now you can't. But really, it's a very, very precious moment, and you need to make the best of that moment.
This is really brilliant. I would like to thank you so much for this point. This is so important, absolutely. Yeah, and so true. So I think two questions left. Maybe the first one about what could be the first applicable application do you think for soft robotics? Because some people ask, still the market, yeah, we have few companies, but if you just anticipate what could be the realistic product for soft robotics that could be used in daily basis, what could that thing you can imagine or anticipate?
I don't know. I really don't know, right? I mean, um, so yeah, the short answer is I just don't know, and I find it very difficult to predict. Um, so one candidate is logistics, but in logistics, it seems like people can afford to structure the environment, to structure the object, to use suction, to do almost anything. Another example is entertainment, especially when it comes to close interaction with humans, right? I mean, there's a huge market for theme parks or for toys, and if those toys can do interesting things um, and are safe, then that's obviously an interesting application. But the price point at this moment is way off. What actually could sell as a toy. So in any one of these disciplines, I think there are significant obstacles that we have no idea how to overcome. And if I add all of this up, I would say I think we need to really mature the technology significantly more before all of these applications become obvious. Now that doesn't preclude some genius somewhere out there of finding the sweet spot and doing that. But if you do that, you'll become rich, right? And that it won't be me. Because I don't know what the right application is.
I don't know if you have any advice. You shared last year advice, but maybe advice you can give to student or maybe junior researcher, maybe something you have taken mind and consider while doing research or maybe in life in general. Advice is very valuable to you.
Yeah, so if you ask me on top of my head, what I would say is that I've observed in the students that are coming in now into the undergraduate classes, um, a big hesitation to act independently. Uh, People are afraid of making mistakes. People are afraid of um, of doing something that doesn't work, right? Of wasting their time, or of doing something where somebody else says, "Well, that was a stupid idea." Don't be afraid, right? I mean, research is a playground, and you should just wholeheartedly enjoy what you're doing, and don't let other people hold you back. I mean, question yourself, doubt yourself, right? Um, Always question whether your ideas are the right ones, but go for it. I mean, if you're being given an opportunity, take it. Don't think twice about it, right? If somebody offers you to give a presentation, you might be thinking, well, do I have enough research to make it interesting, right? Don't ask yourself that question. Just give the presentation. Make it as interesting as you can make it. Gather all the experiences that you can. Talk to people, approach people, ask them questions. Right? Research is about interaction and is about acquiring and accumulating knowledge and experience. And you don't get that by sitting there and waiting that other people are going to tell you things. Right? You need to be an explorer. You need to go out there and discover things. And that only happens when you move yourself. Don't wait for other people to push you.
That's really excellent. I don't know if you have any final words like to say for robotics community. Any final words like to say before closing?
Well, I don't know. I mean, I would say we all live in a very exciting time. I think soft robotics is I always say it's kind of robotics 2.0. It's the way robotics should have been from the beginning. I think it's a very exciting time. I mean, I would appeal to everybody, don't drift away from the robotics community, right? Don't become a separate community. There's tremendous value and potential for the future for us to stay together and to bring all the tools that we develop together rather than, to separate and then years from now to have to work very hard on, on reintegrating the field. So let's stay together and let's change robotics. I mean, I think we're in the process of doing that.
Wonderful. Thanks so much, Oliver. I really enjoyed this conversation. I was so honored to have you. Thanks a lot. Thank you.
Thank you very much for having me.